Welcome to part 1 of our 12-part Explainer series. Today, we are diving into something absolutely fascinating, the architecture of simplicity. We're going to uncover how incredibly simple, perfectly rigid rules actually govern the infinite, chaotic complexity of modern computing. To do this, we'll be looking at the foundation of deterministic execution, specifically through the mathematical syncretism of two absolute giants in the field, John Horton Conway and Donald Knuth.
So let's start with a really big question. How do simple rules create infinite complexity? It's kind of the core puzzle, right? It bridges this massive gap between human abstraction and machine execution. We live in a world that feels increasingly complex, filled with probabilistic AI and, well, messy human thought. But beneath all of that noise, the machines we rely on demand absolute, perfect exactness. So how exactly do we get from a tiny, simple instruction to a globally complex system? To ground this, let's look at a brilliantly simple concept from the cryptographer Nick Szabo. He proposed the everyday vending machine as the ultimate primitive smart contract. Think about it for a second. You put $1 in, you press a button, and a soda comes out. Boom! There is no judge sitting inside the machine deciding if you deserve the soda today. It is purely deterministic. The machine operates strictly on inflexible binary logic that's been translated directly into a physical mechanism. Okay, moving to Section 1, the drive to formalize and how humanity has sought to curb arbitrary authority. Let's see how this builds into our broader historical push toward determinism.
Historically speaking, we've always tried to get away from messy, unwritten human authority by replacing it with strict formalization. And this drive toward absolute digital formalism totally sets the stage for the pioneers of mathematical determinism we're talking about today. The code executes exactly as written. It literally does not care if you had a bad day. If the condition isn't met, the code just halts. That cold, exact execution, that is the absolute bedrock of all reliable computing.
Which brings us to Section 2, Conway's infinite grid and the famous game of life. Our first pioneer here is the brilliant British mathematician John Horton Conway, who built an entire deterministic universe back in 1970.
Now look at the extreme, almost ridiculous simplicity of these rules. Conway's universe is just an infinite grid of square cells that can only be alive or dead. That's it. A cell updates based strictly on its 8 immediate neighbors, what mathematicians call a Moore neighborhood. If a dead cell has exactly 3 live neighbors, it is born. If a live cell has 4 or more, it dies of overcrowding. Less than 2, it dies of loneliness. And that is literally it. Those are the only rules governing this entire reality.
But the contrast of what those rules create is just wild. On one hand, you have a static block shape that just sits there in perfect, unmoving stability. But then, born from those exact same rigid rules, we get Gosper's glider gun, a dynamic, self-replicating machine that continuously fires off moving structures called gliders. It turns out, the game of life is completely Turing-complete, meaning you can build actual working computers inside this incredibly simple, pixelated grid.
Conway proved something profoundly important here. As the philosopher Daniel C. Dennett points out, you really don't need top-down design to achieve computational universality. Highly organized, macro-level complexity naturally and spontaneously emerges from nothing more than the relentless execution of simple, local, deterministic rules.
All right,
Section 3, Knuth's boxes and glue, and the birth of deterministic typography. Because while Conway was building these biological grids, Donald Knuth was facing a massive crisis in mathematical publishing.
Knuth's response to this crisis was to build a pristine, deterministic universe known as TeX. Instead of the localized, messy approach of typical word processors, Knuth completely rejected the norm. You know how most software just uses a greedy algorithm, just cramming as many words on a line as possible and moving to the next, leaving those really ugly, uneven gaps? Well, Knuth, alongside Michael Plass, created an algorithm that dynamically solves a massive global optimization problem. It actually evaluates the entire paragraph at once to minimize visual badness.
He basically translated the highly subjective art of human layout into strict, abstract mathematical objects. Think of it like this. Every single letter is an unbreakable box. Every space between them is a flexible spring of glue. Hyphenations? Those are mathematical penalties. Knuth successfully mapped the highly continuous physical world of publishing into perfectly discrete algebraic symbols.
And the performance is nothing short of astonishing. To put it in perspective, a naive search to find the perfect paragraph layout would take exponential time. You'd be checking every possible combination forever. But the Knuth-Ploss algorithm uses dynamic programming to achieve this global optimization in worst-case quadratic time, or O of n squared. He made perfect, beautiful determinism highly efficient for the machine to execute.
Section 4. The math syncretism between Conway and Knuth. This is exactly where their brilliant minds intersect, building a beautiful bridge between Conway's emergent biological grid and Knuth's rigorous industrial typography.
See, simulating Conway's game of life forward in time is super easy, but rewinding it? Finding out if a specific pattern has a parent or a pre-image? That is a massive combinatorial nightmare. And this leads us to the super cool concept of a Garden of Eden state. It's a pattern that has absolutely no predecessor. It could only ever exist if a human explicitly placed it there at generation 0.
Here is where it all comes together beautifully. Donald Knuth actually used his algorithms to decode Conway's world. Knuth used Boolean satisfiability, or SAT encodings, to mathematically rewind Conway's universe. He turned the physical geometry of the game of life into a massive web of logical equations to definitively prove whether a pattern was a Garden of Eden or not. He literally used the ultimate rigid logic to map the limits of emergent complexity.
And you know, this syncretism goes even deeper. Both of these thinkers united around the creation of surreal numbers, and Conway invented Fractran, proving that Turing-complete universal computing could be compressed into nothing more than a list of basic arithmetic fractions. They both proved mathematically that complex, highly organized systems absolutely do not require complex instructions. What they require is absolute determinism.
Which brings us to our final part, Section 5, Deterministic Execution as the bedrock of computing. Why does all this historical mathematical syncretism actually matter to you right now? Well, because it is the very foundation of everything we build today.
This perfectly highlights the massive divide we are facing today. Think about connectionist AI, these massive language models that are continuous, probabilistic, and heavily prone to hallucination. But contrasting that entirely, we have the rigid, physical reality of the machine itself, the arithmetic logic unit, or ALU. It is discrete, verifiable, and mechanical. The massive challenge of our era is bridging these two totally opposite paradigms.
So how exactly do we do that? We use what is called the semiotic bridge. Strictly formatted text like JSON or your everyday Python scripts, text is quite literally the only safe way to compile our probabilistic associative human imagination into the exact physical electrical behavior of a silicon processor. Ultimately, without this rigid text-based determinism, pioneered by folks like Conway and Knuth, we just wouldn't be able to control modern systems. Cutting-edge frameworks today, like the Yield protocol, use this very concept to pause probabilistic neural execution and hand the state over to deterministic circuits. We are literally forcing the AI into verifiable exactness by making it rely on rigid text. So, as we wrap up this explainer, the legacy of Conway and Knuth leaves us with a critical choice. In an era increasingly dominated by probabilistic noise and hallucinations, we actually possess the tools of determinism. We have the architecture of simplicity. So, will you step up as the author of the machine, wielding strict text to enforce true deterministic fidelity? Or will you just surrender control to the statistical noise? Think about it, because the way we command the future depends entirely on your answer.